Read this phrase. You probably said the cat, but look closer. The middle character in both words is exactly the same. But you didn't even think about it. You saw an H for the and an A for cat. So something weird's happening. To know the word, we need to read the letters. But clearly the letters we see are affected by the word. This feels like a paradox. If you need surrounding letters to know what each letter means, then which one would we start with? How can humans account for both of these things simultaneously? And let's zoom out a bit. When we read cat, we're seeing ink on a page. But now we also have this concept of a cat, the animal, in our heads. What is that on a physical level? How could our brains, made up of biological tissue, produce that much semantic content from something purely syntactical? These questions, how do we settle on meaning, and how does meaning even exist at all, is explored in the book Parallel Distributed Processing: Explorations in the Microstructure of Cognition by David Rumelhart, James McClelland, and the PDP Research Group, with the first edition published in 1986. The example with the cat helps us understand some motivation behind the work. In the real world, even now in 2026, humans are still significantly better than computer systems on natural tasks, like visual perception, understanding language, and retrieving memories, even though biological hardware is slow and noisy. The authors of PDP illustrate that all these tasks share a common structure. These tasks involve the simultaneous consideration of many constraints, where each constraint can be partial, noisy, or ambiguous, but any one of them can be the deciding factor, dependent on the context. In the last video on Hopfield networks, we saw a peek of this, thinking about memory retrieval as the process of a dynamic system. PDP takes that work and pushes it further towards cognition itself, by making parallel and distributed the central design commitments. But that raises the deeper question that this whole video is really about. How can simple units give rise to representations that carry real semantic meaning? At its core, PDP continues the Hopfield-style reframing we talked about last video, with cognition as the behavior of a dynamic system. PDP also tries to further define what a neural network even looks like. At its core, a neural network reduces down to simple units with weighted connections, an activation state for each unit, a rule to update these states, and a learning rule for weights. And in this video, we won't be getting into the math. It's pretty standard for a neural network. If you want a refresher, check out my neural networks video, and definitely watch the Hopfield episode too. I'll link these in the top right. The framing of PDP is very similar to Hopfield's framing. This kind of framing immediately resolves the opening paradox. With the cat, the letter identities mutually constrain one another, and the system can explore possibilities without settling until the constraints line up. So, we don't read letters first and then form the word, and we don't read the word first and then reinterpret letters. Instead, letter level and word level hypotheses interact at the same time. But if the system is this interaction of neuron activity, what in the system is actually carrying any meaning? This is where we, in PDP, dive into the theory of representation. And so far, we've been talking as if a network can have a representation. The network can represent something. But what does that actually mean inside the network? Let's start with the simplest idea of this, where we have a single unit in a network that represents a single concept. For example, a cat unit. Let's assume it's active when a cat is present, and it's inactive when a cat is not present. So very simply, we say this unit is a representation of a cat because its activity correlates with the presence of cats. But is correlation enough? Philosophically, that's subjective, so we can refine this with the functionalist view. Since the unit influences the activity of the network behaves as if the cat is present, so we say that the unit is a representation of a cat. This functionalist framing is not the explicit focus of PDP, but it's the natural bridge to what PDP does focus on: what the network's internal states are, and what it does in virtue of those states. Now let's apply the single unit representation idea to something real. I have a dog named Appa, so under the single unit story, the system, in this case me, would have a single dog unit. But what does that mean? Does it represent my tiny puppy when I first brought him home, or the huge old dog he is now? Does it represent my dog Appa specifically, or dogs in general? I recognize all of these as Appa, but they're wildly different stimuli. This is the dilemma. Either the unit must be very specific, representing or firing for a specific stimulus of Appa, but then we'd have no generality. Alternatively, we could have a very general unit, which fires across many stimuli of Appa, but then we'd have no ability to represent the differences. The puppy and the old dog would collapse into the same representation. With a single unit, there is nowhere for similarity or variation to exist. A single unit only has one degree of freedom. It can answer how much, but not in what way. A single unit only has one dimension. There's very little geometry. Similarity, difference, change over time, these are all geometric relationships, and geometry doesn't show up until you have multiple dimensions. And if geometry only appears with multiple dimensions, then a good representation must exist in multiple units. It has to live in what naturally has many degrees of freedom, the pattern of activation across a population of units. This is what the work calls a distributed representation. A system's representation is a pattern of activation, a vector state. And this is the central idea of PDP. Local representations are the one unit per concept scheme. Distributed representations represent concepts in patterns spread across many units, with each unit contributing to multiple representations. And suddenly, the geometry of this vector and this representational space define the semantics behind this representation. If two stimuli are similar in the real world, they would activate similar patterns in a network, become similar vectors, and therefore be close to each other in representational space. And different patterns become different vectors, sitting far away in representational space. Now that we have this idea of distance, let's explore an example. Imagine we have 5 units in a network, each contributing to one representation. We can imagine a scenario where each unit loosely corresponds to a property. Let's say friendliness, size, fluffiness, energy, and aquaticness. Now suppose the representation of a dog looks something like this, and a cat might look something like this. Immediately, we see this preserves similarity. These vectors are not identical, but they overlap. They share partial activation along multiple dimensions. In a vector space, these vectors would sit close to each other. And let's compare this to a fish. This pattern is very different, particularly in the aquatic and fluffiness dimensions. In vector space, it would sit far away. So similarity in the world becomes distance in representational space. On top of similarity and overlap, let's look at some of the other things this gets us. First, it gets us fuzzy categories. A concept doesn't have to be all or nothing. A wolf might look like this. Not fully friendly, but clearly near a dog. The boundary between a wolf and a dog is not clearly defined. Categories become fuzzy regions, not hard boundaries. And we also have clustering. Dog, wolf, cat, they all sit next to each other. Fish and shark, they're also close to each other. Birds, though, they're somewhere else entirely. Structure in the real world becomes clusters in representational space. But there's a problem I didn't tell you about. We've assumed that each dimension means something, which basically takes us back to the idea behind single unit representation. What about the ideas of friendliness, energy, and so on? Are these really that simple that they can be represented with a single unit? We saw earlier, no, they can't. In neural networks, a single unit rarely actually corresponds to a human interpretable feature. The meaning exists in the collective pattern, not in any individual unit. But we can imagine a scenario where all of these single dimension concepts are also represented with a distributed representation. This simplified example shows that these behaviors are possible in principle with distributed representations. Individual units can participate in many representations, and concepts are realized by many units. This is the whole point. And from here, we can see the rise of abstraction. Lower level patterns, closer to the input, might encode the raw structure of stimuli: pixels, lines, phonemes, whatever. Downstream units can then use this information to build higher level representations and keep abstracting upwards until concepts emerge. Now that we understand this, we can dive into what these representations actually enable. PDP shows that distributed representations give rise to powerful, emergent abilities. These abilities would be magical in a symbolic system, but they come naturally when meaning is a geometry of patterns. The work also shows that distributed representations are more efficient than single unit. If you want to encode a lot of possible states with as few units as possible, distributed encodings blow up the number of possible configurations compared to local codes. We see this even in the simplest binary case. As you add units, the number of possible patterns grows exponentially. And from this, generalization seems to happen naturally. If two inputs activate similar patterns, they'll tend to have similar downstream effects. So the system can generalize to new inputs well, because they naturally land near things the network has seen. Hopfield gave us this initial idea. Distributed representations expanded this into overlap and geometry. But if all of the meaning lies in the shape of the geometry, who shapes that geometry? In a truly intelligent system, we can't have some smart designer to specify the geometry for us. So the system will need to learn itself. The PDP answer, which still dominates to this day, is that we specify what outcomes we want, and the system adjusts itself until it can reliably produce those outcomes. And to do that, the system needs at least three mechanisms. 1. A task signal. What counts as right or wrong at the output? 2. A way to measure error. How wrong was the output, and in what way? And 3. A learning rule. How should the system change connection strengths to reduce error? Basically, a network uses these mechanisms to change its weights so performance improves over many input-output pairs, also known as error-driven learning. If you're still watching this, you might be familiar with this already. PDP contributes what we call the delta rule and general error-correcting ideas, learning internal representations by propagating error backwards through multiple layers, which most people recognize as backpropagation. If you're curious about the exact mechanisms of the delta rule, I walk through it in my first ever video. I'll link it in the top right. And as for backpropagation, there are basically a million deep dives online. So if you want one, I'd recommend 3 Blue 1 Brown's video. I'll leave a link to it in the description. But we still didn't answer the question. How does error-driven learning actually create these internal distributed representations? Well, because the patterns of activity in the network are what determine the output. Optimizing for an output forces the network to create internal states that compress and organize what matters to produce the output. When the network learns, it's not just learning how to produce the right output, it's learning a representational space that makes these correct outputs possible. And, it's important to note, the internal representations are simply built to optimize the task. So like we said earlier, they don't have to be, and most of the time are not, interpretable to humans, just to the network. This is why neural networks are commonly referred to as black boxes. Distributed representations strongly establish the idea that internal representations and the interactions between them are core to cognition itself. More tangibly, PDP is essentially one of the clearest early blueprints for modern AI systems that learn structure inside a high-dimensional representational space. And this is really what deep learning is at the architectural level, representation learning, where systems, like LLMs, construct useful internal vector spaces with distributed representations and transform them layer by layer, encoding meaning through geometry, until the representations become abstract enough to encode language, vision, and even reasoning. This work essentially established the architectural thesis of artificial intelligence that still dominates to this day. Intelligence depends on learned, distributed internal representations, not hand-coded rules. But distributed representations are only part of the story. The engine that makes this scalable is error-driven learning, most famously backpropagation. The work that formalized backpropagation also came out in 1986. called learning internal representations by backpropagating errors. This is distinct from PDP and the idea of distributed representations. Instead, backpropagation formalizes the way that distributed representations are learned, building a space where similarity, abstraction, and simultaneous consideration of constraints emerge as behaviors of the system. And I won't be covering backpropagation at all in this video series, actually, since it's a learning algorithm, not so much architecture. Like I mentioned earlier, I'll link a video in the description in case you're curious. But PDP does leave us with a bigger question, one that's not so much about engineering and more about the philosophy of the mind. If our thoughts are nothing but distributed patterns of neuron activity, what does that say about us? Is the self nothing more than a pattern of physical neuron activity? And perhaps the most unsettling implication of this isn't just that machines might be able to think like we do, but if representation and identity are organizational rather than material, what anchors the self to this physical body? Thanks for watching my video. Stay tuned for my next videos where we'll take this foundation and walk down the pathway to large language models in 2026.